So in this video, we're going to show a few graph problems that are NP-hard. So first we're going to consider three problems. We have largest independent set, which we've seen before, then largest clique, and then vertex cover, which we've also seen before. So remember, a independent set is a set of nodes with no edges between them. So notice here, there's no edges between any of these nodes, and so that's a vertex cover of size 4. A clique, on the other hand, is the opposite. It's a set of nodes with every possible connection. So in particular, for every single node, U and V, in some subgraph, we need the edge between U and V to be in that subgraph. So in this case, the subgraph is these 4 nodes, and for each pair of nodes, the edge between them exists. And so that's a complete subgraph, or also called a clique, of size 4. And last but not least, we have the vertex cover problem, which says we have a set of nodes, and we want every single edge in the graph to touch these nodes. So pick any edge, like this one. It's touching one of the nodes in the cover. Look at this edge, it's touching this edge, it's touching one of them, etc. And in this graph, the maximum size of an independent set and the maximum size of a clique are both 4, and the smallest set of a vertex cover is also 4. So in this graph, we have all 4 of these structures, and all 3 of these structures, and they all happen to have the same size of 4. But maybe it's not a coincidence, and we're going to explore that. So in general, for the clique problem, we have a graph G, and we want to find a complete subgraph, G prime, with k nodes, and each possible edge is between those k nodes. These could also have edges to the rest of the graph, but we really don't care about those. We only care about the edges that appear amongst nodes in the subgraph G prime. So that's our goal, basically find a very large amount. If we think of this as like a social network, this is a large quantity of people such that each person knows another person in the group. They all mutually know each other. So you don't have a situation where your friend group has maybe one person who only knows one of the people. Instead, everybody knows everyone else. So it minimizes awkwardness. So how are we going to prove these problems are NP-hard? Well, we know the independent set problem is NP-hard, and it's a graph problem, so it's a natural choice to reduce from. So to show that these problems are NP-hard, in particular for clique, we're going to show that independent set poly-time reduces to clique. And so what's the reduction? We're given a graph G and a number k, and we're going to create a graph G prime and a number k prime, and we want that G has an independent set of size k if and only if G prime has a clique of size k prime. So there's a critical observation here, which is consider any complete graph has all possible connections. Then what if you considered the complement graph? So if you took this set E, the edges, and you just removed all pairs that existed and added all pairs that don't exist. So essentially, E prime is the set of all pairs, V cross V. So that's all possible edges, and then subtract off the edges originally in the graph. So what would that look like? So if we took the complement, then we would get this graph. Another example, let's say these 2 edges were missing. Then in the complement, we'd have only those 2 edges. So in particular, a complete graph turns into an independent set once you complement it. If you have all possible edge connections, then if you remove them, you have no possible edge connections. So what we're going to do is let G prime equal the complement graph, which is defined to be the graph on the same vertices, but the complement edge set. So we add all the edges not in there originally and remove all the ones that were there originally. So in other words, add all edges not originally in, but remove all edges originally in E. That's what our E prime is. So we create that graph, and we'll use the same K. So K prime equals K. And the reduction idea is pretty simple. If we can find a clique of size K in the complement graph, then that directly translates to an independent set in the original graph. The actual solutions will be exactly the same. It's the same set of nodes. So let's prove this reduction works. So in particular, let's start by supposing that G has an independent set of size K. So I contained in V, some subset of vertices, so that the size of that set is K. And for all U and V in I, we know that the edge U to V is not in I. That's what it means to be an independent set. For any possible edge that could be between nodes in the set, that edge does not exist. And so equivalently, if UV is not in I, that means that UV is in the complement of I. So when I say UV is in I really should say UV is in the edges of I. And so UV is in the complement of the edges of I. Just by definition, if we have an edge, then we don't have that edge, and vice versa, if we don't have that edge, then we do have it in the complement. So this is just by the definition of complement. And so what does this mean? Well, this literally is the definition of a complete graph. So that just means that I is a complete graph. In the complement G bar. In other words, it's a K-clique. So it's pretty much direct. And really, you don't even need to do the two directions separately. This is just an if and only if. So really, we have for any UV in I, for any given I, UV is not in the edge set if and only if for all UV in I, UV is in the complementary edge set. And so we're getting both directions at the same time. So for any set I, if it's an independent set of size K, then it's a clique of size K in the other graph. And if it's a clique in the other graph, then it's an independent set in the original. So these two are actually equivalent statements by definition of the complement. So really, we can just do both of them at once. It's a nice example of when you don't actually need to prove both separately. Okay, so that's the proof. Pretty straightforward, just by definition. And so our reduction, is it fast enough though? So what's the time? Well, how do we do a complement graph? We have to loop through every edge and remove them or add them. So really what we're going to do is loop through every pair of vertices in the graph and check is it in the edge set or not. And if it is, we don't include it, and if it's not, we do include it. So really what this comes down to is we need to copy the vertex set and k. Those are obviously efficient. That's O of v time. But the straightforward brute force construction, you can probably do it in a more clever way, but if we just do it the easiest way possible, we loop over all pairs and do a check. So in the worst case, that's going to be something like O of v squared, because we have a loop over v squared things, and then maybe the check also takes e time. So not the most efficient thing, but it's still poly time. And that's all we care about. So we can do this construction in poly time, and we've proven the reduction's correct. And so we know that independent set reduces to clique, and so clique is NP-hard. So the final conclusion is clique is NP-hard. We showed that it's harder than an already known hard problem. Remember, this means this problem is no harder than this one. So if this is hard, this is also hard. Okay, now let's move on to vertex cover. We can use a similar trick here. So the observation in this case is if you had an independent set in your original graph, so if you had some independent set, there's no edges between those nodes, so every edge has to be somewhere else. All the edges are over here somewhere. So no edges in an independent set implies all edges are somewhere else. In other words, if you had an independent set, I is an independent set, if and only if everything else is a vertex cover. So it's clear that if it's an independent set, all the edges touch all the other nodes. And so if you just took everything else, if you just looked at every other node, well then obviously every edge is touching those things. Because the only way for an edge to be missed is if it was between two things in I, but that contradicts that it's a independent set. On the other hand, if this is a vertex cover, it touches every edge, then we know there's no edges in here. So that's where this statement is coming from. And it's clear if you just look at the picture why that's the case. So what's our reduction going to be? This one's even easier. So G prime is the same as G. We don't have to change the graph. But the K prime is going to be N minus K because it's everything but the independent set, which has size K. And so again, we can prove this as a single if and only if. So because an independent set of size K is equivalent to the other side being vertex cover, will be done. But let's formally argue it. So I is an independent set if and only if, by definition, for every u and v in I, the edge uv is not in the edges of I. Well, this happens if and only if for every edge in the graph that edge must have one vertex, u or v is not in I, because if they were both in I, that contradicts it being a independent set. So let me just say U is not an I, or V is not an I, to emphasize that. This happens if and only if for every edge in the graph, U is in V minus I, or V is in V minus I. And that's exactly the definition of a vertex cover. Is a vertex cover. So here, remember, a vertex cover says for every edge in the graph, either one of its endpoints is in the cover. So it's touched by one node in the cover. So here, for any edge, we know either U is in it or V is in it, which means every node is touching it, i.e. every node or every edge touches a node in V minus I. That's what that's saying. And so if we have a vertex cover, this is true. And then just by taking the complement of the statement, we get this property. So if U is in here, the complement, then by definition of complement, set difference, then U is not in I, or V is not in I. So that's directly just by saying, U is in V slash I, if and only if U is not in I. And that's just by definition of what it means to not be in I. So that part's clear. And so the rest of it follows. So that single chain of if and only ifs proves the whole claim. So again, we get a nice simple proof because the two problems are so related. And obviously, if I has size k, then by definition, the size of V minus I is equal to n minus k, because it's everything not in the independent set. So that part's also equivalent. So really the algorithm is just solve the vertex cover problem on the same graph, but with a much bigger value. And if it becomes true, if it's a true statement, we output true, otherwise we output false. And if we wanted to construct the actual set, what is the actual I? Well, the I is just all the things excluded by the vertex cover. So if we took the vertex cover and removed and looked at what things were not in it, that set is the independent set. So that's how you're actually creating an algorithm to solve independent set using vertex cover. So in terms of if you wanted the solution, which is what you should always think about even though we don't explicitly do it, we take the independent set is exactly the min vertex cover, or the vertex cover computed, everything not in that vertex cover. But the takeaway is vertex cover is NP-hard. Because a hard problem, poly time reduces to it.